Welcome to my third example here in my course with magnetic circuits. Now I have a circuit without the text. In my previous videos I wrote the text, but I didn't have room and space to write the space now. So I'm going to read the text, and basically you can just copy this electric circuit, and we're gonna do the example. So now we have a magnetic circuit here which says that the relative permeability of the ferromagnetic material is 1200. Neglect magnetic leakage and fringing. All dimensions here are in centimeters, and the magnetic material has a square cross-sectional area. Determine the air gap flux, the air gap flux density, and the magnetic field intensity in the air gap. So we have this circuit, and we have to measure and calculate what is the flux, the magnetic field intensity, and the magnetic flux density here in the air gap. So these are the measurements, all are in centimeters. This magnetic circuit has a cross-sectional area, or square cross-sectional area, and I measured what is the area of this magnetic circuit before I before I read the example. And the cross-sectional area of this magnetic circuit is 4 to the 10 to the minus 4 meters squared. Why? Because here, as you can see, the height of this magnetic circuit is 2 centimeters. Now, if you have a square, the square has all dimensions, all the same dimensions. So if you get the height is 2 centimeters, and if it is a square, then this length here is also 2 centimeters. So the cross-sectional area here of the magnetic core is 2 centimeters times 2 centimeters, and you get that's 4 centimeters squared. But 1 meter squared is equal to 10 to the minus 4. 1 centimeters squared is equal to 10 to the minus 4 meters squared. So when you transform centimeter squared into meter squared, you just have to put 4 to the 10 to the minus 4 meters squared. Okay, so the air core is 4 to the 10 to the minus 4 meters squared. Also here you have the length is 2 centimeters, and if it's a square cross section, also the area of this branch here is also 4 to the minus 4 meters squared. Also the area of the air gap is 4 to the 10 to the minus 4 meters squared. Okay. Now, here we have a magnetic circuit, and here is how the coils are wound around this core. So here you have 10 amperes go like this, and it continues to this second current coil, which has the same amount of turns here and here. Now here you will also have 10 amperes go like this. So here you have a current that goes like this, and it's gonna go leave the magnetic path. This is the direction of the current in the second coil. You can just follow this conductors, and you will see that the current here goes in this direction. So what are the directions of the fluxes? Well, if you have a coil, these four fingers, or this second finger, shows the direction of the current, and this right thumb, perpendicular to this finger, shows the flux direction. Also, because it's a linear material, all these units are in the same direction. Here we also have the same thing. These four fingers show the direction of the current, and this right thumb shows the direction of the flux. So now we have two MMF, F1 plus, and we have the second MMF plus M minus. So in these two coils we have produced magnetomotive forces F1 and F2, which is easy to calculate, N times I. Now, what do we have next? We have, well, let me just for a second write down the circuit. Now, we have to know what are the reluctances in this magnetic circuit. So we have this equivalent magnetic circuit. Here we have the MMF of this coil, here we have the MMF of this coil. Here we have the reluctance from point B to E from in the left direction. Here we have the reluctance from B to E in another direction, and here to here we have a reluctance from B to E, and we have a reluctance of the air gap. So here we have the reluctance of B, A, F, E. So we have the reluctance from B, A, F, E. I'm gonna take, well, the sign of the reluctance is something like this. Not usual, not like a resistance in electric circuits, but these curly brackets here. Here we have the reluctance R, B, C, D, A. So from B, C, D, E, we have a reluctance in this branch, and from here to here we have reluctance from B to E, and we have the reluctance of the air gap. Now we are going to measure the reluctances of this. We're going to measure all the reluctances in this circuit. So how do we measure B, A, F, and D? Well, we have to know what is the mean length, or the middle line length of this particular branch, and we are gonna calculate that analytically. So here is the middle line, and from here to here we have 1 centimeter plus these 50 centimeters. From here to here we have 50 centimeters, and from here to here we have 1 centimeter. We are in the middle, we are calculating the length of the middle line. So it's equal to 1 plus 50 plus 1. Now we measured in the upper branch the length here. Now we have to measure from here to here, which is the same thing. From here to here we have 50 centimeters plus 1 millimeter here and plus 1 millimeter from here. And we get 1 plus 50 plus 1. And from here to here is the same length as here, so that's 1 plus 50 plus 1. Okay? 52 plus 52 is 104, and plus 52 is 156 centimeters, which is equal to 156 times 10 to the minus 2 meters. Okay, but as you can see, from B, A, F and D, it's the same length as from B, C, D and D. So the length from B, C, D and D is equal to 156 times 10 to the minus 2 meters. Now from B to E we have 50, but here we have an air gap of 0.5 centimeters. So we have 50 minus 0.5 centimeters plus 1 millimeter and plus 1 millimeter here, and length from B to E is equal to 51.5 10 to the minus 2 meters. Because it's, if you don't look at this air gap, it would be 50 plus 1 and plus 1 here, and it would be 52 centimeters. But minus this air gap, we get 51.5 10 to the minus 2 meters. And the length of the air gap is equal to 0.5 centimeters, which is equal to 0.2 10 to the minus 2 meters. We have to transform all the units into basic units, and basic unit for the length is meter. Now we can measure the reluctances of this magnetic circuit. Is equal to, well, the length of the LBAFE is equal to 156 times 10 to the minus 2 divided by the permeability of this material is equal to mu r times mu 0. That's equal to 1200 times 4 pi 10 to the minus 7 times the area of the cross-sectional square cross-sectional the square cross-section of this magnetic circuit, which is equal to 4 times 10 to the minus 4, and that is equal to 2,58 times 10 to the 6th ampere turn Weber. This is the unit for the reluctance. Well, the reluctance of BAFE is the same as the reluctance of BCDE because the length is the same, the cross-section area is also the same, and the permeability is the same. So is also the same value. need this. The reluctance RBE is equal to the length divided by the permeability, which is equal to 1200 times the mu 0 is a constant 4 pi 10 to the minus 7 times the area of the cross section times the area of this branch here is 4 to the 10 to the minus 4, and you get that it is equal to 0.82 times 10 to the 6th ampere turns Weber. And the reluctance of the air gap is equal to the length of the air gap, 0.5 times 10 to the minus 2, divided by, well, the permeability of the air gap is just mu 0, 4 pi 10 to the minus 7, times the air gap is also the same as the air gap of the core, and that is equal to 4 times 10 to the minus 4. And that is equal to 9,94 10 to the 6th ampere turn Weber. Now we have measured all these reluctances of the magnetic circuit. Now we can measure the fluxes in that magnetic circuit. You know that this coil will produce a flux that is going to go like this, and this coil is going to produce a flux that is going in this direction. Here, these flux in this node are going to compute each other. You have to add this. Here in this branch you will have a flux that is equal to the sum of these two fluxes. Like in electric circuits, it's also the same, and it is equal to this flux, which is also the flux of the air gap, is equal to the sum of these fluxes that go in the volt node. So that's the Kirchhoff's current law. Also, it's the analogy to the Kirchhoff's current law, which states that all these magnetic fluxes that come into this node, the amount of these fluxes that come into the node have to be the same as the amount of fluxes that comes out of the node. So flux in the air gap is the sum of flux 1 and flux 2. So we have to calculate what are the flux 1 and what is the magnetic flux here too, so we can measure the flux in the air gap. Now what do we know? We know that the flux 1 and flux 2 is the same because there is an equal number of turns here in this coil and here. The same current goes, and in their branches the reluctances are the same. So flux 1 and flux 2 are the same value. Now we can do the closed loop equation for this and this. That is also the voltage law of the electric circuit. Same analogy. So here we have F1. We're gonna do the equation for this closed loop. And we are going to do the equation for this closed loop. So for this blue closed loop, the equation is that the MMF is equal to the all magnetic dropouts, I would say something like that, is equal to flux 1 times the sum of this RBA, the RBAFE plus RBE plus RG. Plus the MMF, the dropouts of this flux 2, and it's equal to so this is actually the same as you would do with the electric circuit. This is the voltage and this is the voltage dropouts of the closed loop of this side. Now, this is the magnetic dropouts. I don't know, there are no particular name for it, but it's the same analogy as the as you would do with the electric circuit. F2 is equal to flux 2 times the sum of these reluctances, the reluctance of B, C, D, E plus the reluctance of BE plus the reluctance of G, and that the air gap. So you write like this. Plus the magnetic dropouts of this flux 1 so these are the equations for these closed loops. We have everything here except flux 1 and flux 2 and flux 1. We can easily calculate that F1 and F2. If you watch my previous videos, you can act F1 is equal to N1 times I, F2 is equal N2 times I. They are the same. You know that the flux 1 and flux 2 is the same value. You know you have all the values of the reluctances here, and I'm just gonna skip the calculation of this. I'm just going to show you what do we get for flux 1 and flux 2. This is a simple equation, but I'm gonna skip that, and you get the flux 1 is equal to the flux 2 and is equal to 2.067 times 10 to the minus 4 Webers. So the flux of the air gap is the sum of this flux 1 and flux 2, and it is actually this time the double value of this. I don't need this anymore. You can copy it and write it down. I don't need it anymore, because I got the values of the flux 1 and flux 2. You got the equation and you can do it yourself, but I just skipped that because that's more math, not physics. And the flux in this air gap is equal to the sum of these fluxes. Flux 1 times flux 2, flux G is equal to 2 times flux 1, because flux 1 is equal to the flux 2, and that is equal to 4.134 10 to the minus 4 Webers. Now we got the flux, magnetic flux here in the air gap, because this F flux G is going from here to here, the same amount here and here. If you neglect fringing and leakages. Now the magnetic flux density is equal to flux of the air gap divided by the area of the air gap. That's 4.134 10 to the minus 4 divided by this, because AG, the air gap of the area of the air gap, is all the same as the area of the core, and you get 4.134 10 to the minus 4. This deletes each other, and you get something about 1.034 Teslas. So the magnetic flux density, this is usually a high value, is equal to 1.034 Teslas. And magnetic flux intensity is equal to mu0 times the magnetic flux density, because in the air gap the relative permeability of the air gap is 1, so you write just this, and the equation is wrong, because it is equal to magnetic flux density divided by mu0. Sorry about that. And you get 1.34 Teslas divided by 4 pi 10 to the minus 7, and is equal to 0.822 times 10 to the 6th ampere turns meter. So now we got what we wanted. This is now we now calculated these values, and that's it for this example. See you in my next video, which is going to be a theoretical video, and I'm going to show you what is the inductance. That's going to be a short video, fortunately for me. See ya.